All right, we're going to start talking about another kind of reaction. We're going to talk about acid-base reactions for a little while. Um, but before we dive into the reactions, we want to talk a little bit more about acids and bases in general, right? We've kind of hinted at these before, but let's just make sure we're all where we're supposed to be here. Okay, get us a little bit more detail and information on what's going on here. Um, There's just some general ideas here. Acids tend to taste sour, while bases taste bitter. Bases feel slippery, right? Most soaps end up being bases. Bases will dissolve fats and oils. Makes sense that there would be good soap products then. Um, Acids tend to react with metals to give off hydrogen gas most times, and they'll conduct electricity in solution. And we've talked about pH scale and knowing about approximately where things are. Things that are acidic have a low pH, and things that are basic have a high pH. So acids are down here, and bases are up here. All right. Um, let's refresh our brains here about strong electrolytes. Remember, strong electrolytes dissociate completely into ions in solution. This is when they're dissolved in water. Okay. We said all soluble ionic compounds are strong electrolytes, as are all strong acids. We said you had to memorize these dudes. There's 7 of them. Okay. Um, the strong bases are also strong electrolytes. And I didn't make a huge deal about memorizing these simply because the strong bases are all soluble hydroxides. Okay. Because they're all soluble hydroxides, you'll have a list of these given to you on the exam on the info sheet. So just pay attention. Okay. Um, Hydroxide ions that are soluble are all of the group 1As, calcium, strontium, barium, and ammonium. Ammonium is not a strong base, but the rest of them are. And so you can see them right here. Here's the group 1As. Here's calcium, strontium, barium. They're all given to you. So just remember to look for them, and they're all strong bases. Okay. In a previous video, we talked about Arrhenius. This is what we had said before. Arrhenius acids dissolve in water and produce hydrogen ions or protons or hydronium ions. Bases will dissolve in water and produce hydroxide ions, right? We saw those happen. Okay. Um, but the downside of Arrhenius is that some bases, is it bases or is it acids? Some bases do not have hydroxide or don't make hydroxide. And so we want to think, okay, we need to expand our definition a little bit. And it was these guys, Bronsted and Lowry, came around and gave us a new definition or an updated definition about what acids and bases are. And they came at this from the idea of a proton transfer, meaning that an H plus ion is moving from one thing to another thing during a reaction. Okay, so if we look here, we have water and we have ammonia. And what happens is one of the H's from water gets grabbed by the lone pair on ammonia and turns into ammonium and hydroxide. Okay, so ammonia does the proton transfer, so it acts as a Bronsted Lowry base, right? The base is a proton acceptor, but it also produces hydroxide, so it is also a not Lewis, gosh dang it. It also is an Arrhenius base because we've made hydroxide. Okay. If we look at HF, which is what this guy is, okay, we'll react with water. Again, what we see here now is a lone pair on the water will grab the hydrogen off of HF to make hydronium. This is our H3O plus, and leave behind an F minus. Okay, this is again a proton transfer. Right here, HF is acting as an acid because it's donating its hydrogen. So acids donate a proton, bases accept a proton. Okay, that's our Lewis definition of this. I'd also want to remind you that H plus and H3O plus in solution are roughly the same idea. Okay, both of these are weak, and so we're using our weak electrolyte arrow, our equilibrium arrow, to accomplish that. Okay. One thing I want to point out here is that the Bronsted Lowry definition is not just limited to things, excuse me, things that are aqueous, but we'll use this a lot in terms of organic chemistry as well. So we'll circle back to this several more times in your career. Um, but for now, we just want to leave it kind of where that is. Okay. Most things that we've looked at up until this point are what we call monoprotic acids, means they have one hydrogen to donate. So we saw HCl, right? HBr has one hydrogen. HF has one hydrogen. So most of the things, right? Acetic acid, right? Remember the H in the front is the acidic hydrogen. The rest of this stuff on the end is not. And if we remember, acetic acid looks like this, right? Only the OH here, this hydrogen is this hydrogen. That's the acidic hydrogen. These guys out here don't do anything acidic or basic. And so this is still a monoprotic acid. So monoprotic is just one hydrogen, and most acids are this way. We also have diprotic acids. We talked about sulfuric acid. That's one of those, H2SO4. Other examples, H2C2O4, oxalic acid, or carbonic acid, which we'll talk about in a little bit. Have two ionizable hydrogens. Remember we said that sulfuric acid is one of our strong acids, and it dissociates completely for the first ionization and makes the hydrogen sulfate ion. Okay, this is known as an acid anion. Okay, because it still has an ionizable hydrogen to it. So the next ionization would be the HSO4 minus, donating its hydrogen to make H plus and a sulfate. The sulfate itself is not an acid anion because there's no hydrogen involved in there. Excuse me, at all. Shoot. I should fix my arrow here because only the first one is strong. Okay, come on, PowerPoint, behave. Only the first one is strong. The second one is weak, and so this needs to have our equilibrium arrow that's pointing in both ways. Okay. Except for sulfuric acid, everything else would have a weak dissociation for both things, right? We can also think of this as, because it has two hydrogens to donate, that we'll see both of them dissociate in reactions to do things, right? So when we use sulfuric acid, we can write a net ionic for that that looks like this. Because in a reaction, sulfuric acid will probably do this, okay? And we'll circle back and see some more of that as we do some other stuff, okay? Anything else that has more than two ionizable hydrogens we'll refer to as a polyprotic acid. Um, we'll look at specifically some triprotic acids, but there's not a lot more that have more than one. These are things like phosphoric acid, okay, arsenic acid, uh, and so on. A lot of organic acids will have that. Citric acid, for example, is H3C6H5O7, right, with three ionizable hydrogens in the front. These are all, oh, excuse me, triprotic acids, which means we can take off each acid, each H plus in sequence, right, if we're careful with it. H3PO4 aqueous will dissociate and it looks ugly. Will dissociate and give us H plus aqueous and H2PO4 minus aqueous. Notice our H2PO4 minus is an acid anion and will dissociate again. right? Each one of these is weak. We're going to talk a lot about this in Gen Chem 2 as well. So um, we'll get more detail. HP. Come on, mother. There we go. All right. HPO4 2 minus, which still has a hydrogen involved, and so we can dissociate one more time. HPO4 minus, give us one more hydrogen and a phosphate. Once we get to phosphate, we're out of hydrogens, and so we don't do any more dissociations. We'll talk a lot more about this in Gen Chem 2 when we get to it. Okay, but for now, I just want us to recognize how many ionizable hydrogens are there as we're doing stuff. Maybe write a dissociation for it. Okay, let's take one more step. We'll talk about weak bases. Weak bases are weak electrolytes. Remember, our strong bases are the ones that are the soluble hydroxide compounds. We said that at the beginning. The weak bases are organic compounds that contain nitrogen. Okay, for the most part, we're gonna, yeah, right, and they're all gonna react in similar patterns to ammonia, and we kind of saw this already. For example, if we had methylamine, or maybe let's do it with dimethylamine, CH3 2NH. It has a hydrogen on it, but it's not acidic. Right? These work by reacting with water. This is the same thing that ammonia does, right? It's going to give us CH3 2NH2 plus aqueous and OH minus aqueous. Okay, so it's Arrhenius because it produces OH minus, but it's also a Bronsted Lowry situation because our nitrogen has picked up a hydrogen when we do that. Okay, so anything that's organic-y that has a bunch of nitrogens, right? We saw pyridine before, C5H5N, right? CH3NH2 or CH3CH2 3N, right? A lot of these things look all the same, but it's all because this nitrogen that's like ammonia has a lone pair on it, and that lone pair takes the hydrogen off of the water. Okay, we could look at it this way. Don't do this. Right, if we draw our water out, right, we can say, okay, that this lone pair grabs this hydrogen and this bond turns into a lone pair. I'm probably getting away from myself here, but whatever, I had room. We'll make ammonium and hydroxide. All these things would be aqueous. This is a weak electrolyte situation. This is actually an organic chemistry perspective of putting things together, but it gives us that idea of what we're looking for. Okay, really, I just want us to be able to recognize weak bases. We'll talk about dissociation stuff. We'll revisit this in Gen Chem 2. The next video, we'll talk about neutralization. I'll show you an example of neutralization with a weak base, and we'll be good. Okay. If you need me for anything, let me know. Ask questions. I'm here for you, and I'll see you in class.